Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. In one of the previous videos, I had reviewed this one. This is an SAF Spectrum Compact Spectrum Analyzer. This particular one operates in V-band, that is between 56 to 67 gigahertz, and of course it has a waveguide interface. And to the waveguide interface, you can connect various antennas and attenuators and so on, and you can even go back to coax if you really wanted to. And we did an extensive review on this. I did a full teardown. We looked at the GUI, the software. We did a bunch of wireless measurements. We did some PC interface software measurement with it as well. And we basically figured out how well it works. It boots up instantly. I like the GUI. It's built like a brick, full aluminum chassis. So it's a fairly unique instrument. There are not that many compact spectrum analyzers like this on the market. It did also have some limitations in terms of the minimum span and the resolution bandwidth it could offer. It had a charging port and a micro USB as well for both computer interface and of course charging the internal battery. So we did an extensive look at this, but of course they have a whole bunch of other products as well in the same spectrum, compact spectrum series, and they cover pretty much every frequency you would want. And I have here a Ka band version. This one works from 24 gigahertz to 40 gigahertz, although there is another newer version on the website that goes from 24 gigahertz to 43 gigahertz. So this one targets all of the 5G bands. All the millimeter wave 5G bands are covered in this. So with a single instrument, you can do a whole bunch of wireless measurements if you're working in that industry. And this one is of course an unlicensed band in the 60 gigahertz band. So they've basically broken the bands into applications. Depending on what domain you're in, you would be picking up one of those or maybe multiple of them. With the coaxial input, it gives you also flexibility. You can have antennas, you can have coax attenuators, or you can just go back and keep everything in coax. So depending on what you want to use, one may be more convenient than the other. The waveguide, of course, above 60 gigahertz is fairly convenient to use. This also has a few additional benefits. Its minimum frequency span is now 10 megahertz, which is much better than the 1 gigahertz this one offered, and it also has resolution bandwidth control from 100 kilohertz to 1 megahertz, which is also new, which is very, very nice. Now, in terms of charging and communication, there is now only one USB-C port, which is much, much better than having two ports to charge and control the instrument, because you don't have to bring a charger with you. You can pretty much use any USB-C to charge this. So I just want to give you a very quick overview of the GUI, show you a couple of the features, but really you should be watching this one as well in case you want to see what's inside of it and look at all the different experiments you can do. And then we're going to do some interesting measurements with this one in the lab. Let's go ahead and turn the instrument on and take a look at some of the GUI features here. So I'm going to turn it on, and as you can see, it boots up essentially instantly. This is exactly the same as the E-band version of this unit, and you're going to get a very consistent GUI experience across all the compact spectrum units, which is nice. The only change I would make in the case of the GUI here is I would make this font a bit larger. There's no reason the font is so small. The buttons have quite a bit more room on them. There is a high contrast mode. It helps in some scenarios, but I like the colors. And you can, of course, rotate this, and just like the other one, the GUI will rotate. I like this orientation as well. So in terms of some of the features of the GUI that makes it easy to use in the field, especially if you're wearing gloves. For instance, if you're on any of the settings, some of the buttons are always red, which means that you can't press them because those entries will be invalid, and this will dynamically change. So let's say if I want to change the center frequency, as soon as I press 2, you get some other buttons that show up, and then you can always cancel, or if you make a mistake, you can delete. But because the buttons become disabled, the ones that you cannot enter, that reduces the chance of edits you have to do. And if you're wearing gloves or you have big fingers, that can be quite annoying. So this is a nice thing that they have across all the units. In terms of some of the new features in this version, the Ka band, which is not available in the E band, has to do with the architecture of the unit. We'll see that when we take it apart. Now we actually have resolution bandwidth from 100 kilohertz to 1 megahertz, and video bandwidth from 1 kilohertz to 30 kilohertz. You can always, of course, leave them on auto. This is very useful because before we didn't have this capability and we were stuck at a particular resolution bandwidth, and that would mean that very fine tones that are spaced apart, you would not be able to distinguish them. So now we would be able to do that. We'll take a look at it in some of the experiments. Also, in terms of span, this instrument is quite a bit better because the span here, in the minimum span of the E-band instrument, was 1 gigahertz. So you couldn't look at a narrower span. In this case, you can go all the way down to 10 megahertz. As you can see, it would sweep very fast in a 10 megahertz span. And combined with the resolution bandwidth of 100 kilohertz, we should be able to see some nice fine details in the spectrum. And I'm eager to take a look at it. So this is getting much more like a regular spectrum analyzer, despite its size and being so portable and having such a lightweight firmware running on it. And you still have all the markers and all the trace capabilities. You can have averaging of the traces, you can have cumulative traces and maximum hold, and we've done these experiments before. It's essentially the same. You can average them as well. You can measure in-band power. This can be pretty handy if you have multiple tones. If you have a modulation, you want to find out how much power you have, you would be able to do that as well. There's a full screen, the same as before. Now under the tools, we do have now a couple of other additions. We have the path calculator. So there's a freeze equation calculator directly built in here. If you're in the field and you know a distance to the antenna and you're measuring some power, you want to make sure if this makes sense from where you're standing, you can quickly enter those numbers and find out what kind of numbers you're supposed to be getting. So if you have an antenna connected to this, you can enter the gain of the antenna. If there's a dish somewhere where you know the gain, you can do that. So it's nice to add this to it. Other than that, it's really straightforward. It's exactly the same as the compact spectrum E-band version, nice and easy to use, quick, and I'm eager to try that. So I have a couple of experiments that I have put together. I think we should jump there. Before we do the experiment, actually, I want to show you what's inside it, because it will give us some insight on the architecture, and then we can see if the measurements and the architecture are kind of consistent with each other. So let's go ahead and see what's inside the unit. So let's take a look at the architecture of this instrument and compare it with the E-band instrument that I did a full review and teardown of before. So here are the boards for the E-band instrument, and here are the boards for the Ka-band instrument. And you can see the architecture is very similar. We still have a fully digital section here which connects to the LCD, to the battery, to the USB, and so on. And then we have the RF portion. Now in the E-band instrument we had an RF section and an IF section. So the synthesizer, the LO, as well as the IF handling and the power detectors were done on a separate board, and we had one enclosed section for the RF. It seems that they have been combined into one section here. So the architecture is most likely still very similar, but of course there are major differences in terms of how the signals has to be routed. This thing has a waveguide interface, this is coaxial, so there will be some changes. I suggest that we take a look at this and compare them and see what they have changed. So just a quick reminder here, in the E-band instrument there was a single front-end RFIC, which is wire bonded, and then we have a coplanar waveguide to waveguide transition, and what comes out of the other side is a waveguide flange. The LO would come in, become differential, and go into the chip, and there's most likely a multiplier directly on the RFIC, and the IF coming out would then be split into two. Those two sections would then go into a SAW filter, and on the other side they would go into a whole bunch of logarithmic power detectors. So it seemed to me that they had a low band and a high band power detector section, and they were comparing those results to figure out what the spectrum looked like. At least that was kind of my reverse engineering on the spot. They did also have an entire PLL section where the LO was generated, amplified, and passed on to the other board. So clearly these two have to be combined in some way in the new architecture here. So let's put this aside. Let's go ahead and open this and see what's in here. I've already taken the screws off. Let's be careful here in case there is some wire bonding. Okay, there it is. You can see it's very nice again, and I don't see anything RF on this side yet. Let's zoom into this a little bit more. So it looks like on this side of the board we don't really have any RF components. I don't even see the trace, so it's most likely on the other side. I do see some DC-DC converter portions here, and these signal conditioning and power supply and so on are of course going to be needed depending on what's on the other side. So let's go ahead and carefully remove this and flip it. Oh, look at that. That looks very nice. And oh, look at this. There are no IC markings anymore. Yep, everything has been either machined off or laser etched, or it has an epoxy on it. So that's going to make things a little bit more interesting. Let me go ahead and put this on something. And by the way, here's the chassis. You can see RF absorbers, various locations. It's a very common technique. I'm going to put something underneath this so that it would stay level, and then we can do some analysis on it. Okay, let's see what we can decipher here. So this board has a couple of different sections. We can analyze them in turn. There's a section here which is almost certainly digital. The only chip in this entire board that has a label is this one. This is a microchip I/O expander IC. This allows you to use very few microprocessor IOs to control many things. It's a very common block used all the time in systems like this, because there are so many things that probably need to be controlled here with digital logic. So if you start from here, the only thing we see that's recognizable right off the bat is a TCXO. So we have a crystal here. This is most likely a voltage regulator for the crystal. So this crystal is going to be our reference. This is most likely the reference for the entire LO architecture. The output of that goes into this chip, and then this chip, and this chip are all connected. Now take a close look at the output of this one. We have a Wilkinson power splitter. This is the only RF component on the board currently that I can see, and there's actually some filters here too. We'll take a look at that. So this Wilkinson power splitter will split the signal into two ways. One goes left and one goes right. So therefore, it is very likely that this is a VCO. So this VCO output comes over here, gets split. This is probably a divider of some kind. It will be a divide by 4, divide by 2. And the output of that goes into this chip here. Now this chip is going to be our PL up, which means that the reference comes in here, the divided down VCO comes in here, and this guy will control the VCO, closing the loop and creating a PLL. The other side is going to have an amplifier most likely, and this is going to amplify the output of the VCO to a very high value, compensating also for the losses of this Wilkinson. And then there's a chip afterwards, which is a little bit of a mystery. This IC could be an attenuator perhaps, maybe a gain control block, so that you can have a constant LO amplitude across the entire frequency going to the mixer. That's probably what it is. There are several other possibilities. Of course, it's hard to know without doing some measurements on this. We have over here our RF coming in, and this is a southwest edge connector. This is a very, very high quality connector. This in fact are metrology grade for edge connecting to a board, and that brings you into a coplanar waveguide. It's from coax to coplanar waveguide transition going into one chip here, which is also a mystery. Now depending on what's in this mixer chip here, and I said maybe it could be their own IC, it could be something from Analog Devices, I'm not sure. But if this has its own LNA and it has its everything built in, this could simply just be an attenuator or some kind of a protection circuitry. Whatever it is, the combination of this guy and this guy is our RF front end. So the LO comes over here, the RF comes over here, and the IF comes out. And this IF coming out is going to be at some offset in frequency, not so high, but nonetheless it's going to not be at DC. So the output coming here, we can see some bow tie filters over here, and then it goes into this inductor. So on one side, we have the signal coming over here, going into the SAW filter, and then coming into this section. And the other side, we have it also going over here at the same time. So this reminds me of the old architecture, I should say the architecture of the E-band circuit, because we also have two different sections, one with the SAW filter and the other one at very low frequencies, and then we had a bunch of power detectors on the other side. Now, this seems to be a bit more complicated. There are a few more ICs here. Certainly some amplification is going to be there, so that op-amp that we saw in the other board may also be present here, and some power detectors as well could be there. I don't think there is any major analog to digital conversion, because anyway there's really no way to pass that data forward unless it's happening at a very low rate. Either way, the power detection section is going to be more complex than the E-band, because this instrument gives you resolution bandwidth control, which is a huge advantage over the other one. And the smallest sweep that you can do is now 10 megahertz, which is also a huge advantage compared to the E-band version. So it's certainly more complicated. But from a design point of view, it looks very nice. Again, using very high-end components everywhere where possible. I can't tell exactly what components these are, but if the other one is any reference, they're all going to be very good. So from the other side, as I spoke a little bit earlier, nothing really surprising, just a couple of voltage regulation sections and so on. And these connectors are quite expensive, and you can see they're manually attached to this. And I don't think they reflow this. You don't have to reflow them, but you could. And yeah, it looks very nice. So I think we have a fairly good idea of the RF section. Let's take a quick look at the digital section, because there's some changes on that as well. One other quick thing I wanted to point out, the structural integrity of this connector is determined by how well it's attached to this. And if you look, aside from it being attached to this board, of course, the two screws on each side are much larger, allowing you to compress down and hold this in place. So that's going to be very good. So they've paid a lot of attention to making sure that this connector lasts a very long time. And another really nice thing is that if anything happens to this connector, changing it is very straightforward. So this means that you wouldn't have to worry about, for example, if this guy breaks and your entire unit becomes useless. It's not the case. It should be fairly easy to change it. And here are the two digital boards. You can see that they look very similar. In fact, this is the E-band, this is the Ka band. One major change in the Ka band is that it has a USB-C. It no longer has a micro USB, and the charging is also handled through the USB-C. It doesn't have another external charger. Thank you for that. This is so much better than having to have another power supply with you. When one interface controls everything, that's the right way to do it. I wonder if they've made those changes for the E-band or not. I'm not sure, but certainly this is an improvement. Other than that, memory and the same ARM processor from SD are present. Micro SD card. This most likely goes to the battery. They've changed that. The protection circuit over here is slightly different. And there's some USB controllers there, same USB controller over here. Yeah, looks very similar, nothing unusual. The processing power is going to be the same. The GUI is essentially the same across all the different models. So I'm quite happy with it. I like the power button with the two LEDs on each side that shines on a silicone button from the outside, and I think that's very clever. Other than that, looks very good. Let's go and do some experiments with it now that we understand how it works. So let's take a look at this antenna array that we're going to use for our testing. This is a 9000 element patch antenna array operating at 38 gigahertz. And before you get too excited, it's not really that impressive. The losses of these traces is not very good, and this material, the copper, is not finished, so it's got now very bad surface roughness. It's going to have fairly high loss, and these antennas will have beam that steers across frequency, so you really don't want to use it across a wide band. This is only supposed to be used at 39 gigahertz. The input is right down the middle, and you can see that we have a distribution network to 9,000 of these patches. This antenna is also really old, probably over 20 years old, and there's some defects on it. You can see some of the traces have been damaged, so its performance is certainly not going to be great. On the other side, we have a waveguide interface, which is exactly the kind of waveguide interface we need for this kind of experiment. So what I want to do is just find out how much power comes out of this in terms of antenna gain. I want to measure, see if we can estimate the gain of the antenna and see if we can find one of its side lobes using the instrument. This is going to have a very, very narrow beam, so maybe we just measure the beam width, for instance. It would be another thing we can try. So let's go ahead and put this in a setup and see what kind of behavior it has. So for our transmit site, we're going to use this as the configuration. We have a doubler here. This is going to convert the signal multiplied by 2 and then put it onto a waveguide. This is a 10 dBi antenna, so that's going to radiate out away from the table. We have the signal coming in from here, of course, so we have an amplifier here which drives this millimeter wave module, and then we have a synthesizer here which provides a signal. I've done teardowns and reviews of most of these components, so you can certainly find them on the channel. But the power coming out of here at this edge is roughly about minus 10 dBm. It's not very accurate simply because this hasn't been calibrated, but we do have a 10 dBi antenna. So we have some idea of the transmit power and the antenna gain. So let's take a look at the receiver. And on the receive side, we have our patch antenna array, and the waveguide comes out and gets converted to a coax to directly the input of the compact spectrum. So here we would be able to measure this, and of course this is a wireless link because on the other side is pointing to our transmitter, which I just showed you. So we should be able to get some characterization going. So let's try and do some measurements. So right now we're in full span from 24 gigahertz to 40 gigahertz, and we do see a tone at around 38 gigahertz here, and we also see a tone here that shouldn't actually exist. That tone is not really there. So we're going to go back over here, and we're going to go under Tools and Settings, and we're going to go under Settings. We're going to turn on the signal ID. And by turning on the signal ID, hopefully we will be able to eliminate that. There you go. As you can see, it's no longer measuring that tone, but of course our tone at 38 gigahertz should still be present. So let's wait a little bit. It takes a while to sweep in full span at 1 megahertz resolution bandwidth, but we should see our tone. There it is. Our tone is there, and the other spurious tone is gone. Good. Of course, we're looking from so far away. That doesn't really help us. Let's go ahead and change the frequency. I'm going to put the frequency center at exactly 38 gigahertz. There we go. That's our 38 gigahertz. So right now we see our main tone in the middle. That's perfect. That's what we're looking for. We're still looking at a huge span. So I'm going to look at the span here. It's a 4 gigahertz span, and thanks to this instrument we can go to a tiny span as small as 10 megahertz. Let's go ahead and try that. Minimum span. There it is, 10 megahertz, and you can see that the signal is not actually a CW tone. And looking at very far away was misleading us into thinking that we were looking at a single tone. Indeed, this is a tone that's sweeping, and looking at its behavior, it's clear that it's sweeping in a ramp configuration. The frequency goes up and then jumps back down. And every time it jumps back down, it generates some spurious tones, and that's because the PLL of the synthesizer has to relock, and it may momentarily create a tone we don't want to. So all of these characterizations are not possible because we can have much smaller resolution bandwidth than we used to. And you can see that both the span and the resolution bandwidth are now set to 100 kilohertz, and that's pretty useful. So that looks good, but now of course it's moving around, so the center measurement no longer gives us the total amount of power that we're interested in measuring. So why don't we go back over here and do an in-band power measurement, and we can change the bandwidth of the in-band measurement, let's say to 5 megahertz. There it is. So now we can see a 5 megahertz band for which continuously the total amount of power is being displayed at the top left there. Now we can see the total power being received by our instrument, which is about minus 50 dBm. So I would like to find out from this measured power, the fact that I know how much power is on the transmit side, what is the antenna gain? Now I can go back over here, and actually use one of the tools that are built in here and do a path calculation. But unfortunately, this path calculation tool does not allow me to make the distance less than 100 meters. It's only given in kilometers. Now I would like to be able to enter, 2 meter, 3 meter, 4 meter distances, which is what you would expect in the lab. But because this is designed for outdoor usage, they're really not thinking about doing measurements less than 100 meters, because it's unlikely that you would be closer than that to your transmitter. And anyway, the dynamic range of this instrument doesn't allow you to put a lot of power in it to begin with, so you can't be that close. But it'd be nice to have this so you can enter a few meters as well, especially because at a couple of meters you're really sensitive to the distance. But we're about 2.5 meters or so from the transmitter, and the free space path loss in that case is about minus 72 dB. So we lose 72 dB of signal just between these two transmit-receive modules at 38 gigahertz. Now we know the transmit power, it's about minus 10 dBm. We know the antenna gain is about 10 dB, so we have a 0 dB plane at the transmitter. 72 dB down, and we're measuring about minus 50. There's some additional losses in the cables and the converters, so the antenna gain may be somewhere between 25 dBi to 30 dBi, which is not very good for something that has 9,000 patches. Again, it's old, the surface is bad, some of the traces are cut, and that's going to all reduce the performance. Now going back again, you can see some of the other tools built into this. You can do masks, you can record what you're measuring, you can timestamp it and put notes on it so that you know where you did this measurement. But all of these new capabilities from the GUI are on top of what I showed you from the previous instrument. So they've certainly improved it, and I'm sure they continue to improve it, and I will update the firmware as they become available. And let's do a couple of tests with the markers and detectors as well as the trace type here. So right now we have the detector type set to average, and the trace is normal, which is a regular sweep that you would get. But I'm interested in seeing some of these spurious effects and actually catch them, especially if you want to save it and record it and analyze it later. So we can go ahead and put a max and min hold type of a trace there, and this is very handy, especially if you have a modulation. You can see what happens when the signal is at this minimum value. In this case, this minimum signal value is just a noise floor there, and the white trace is the actual measurement trace, but the blue is of interest. It shows us that the sweep is exactly 2 megahertz, but not only that, we get a lot of spurious tones that occasionally appear in the spectrum. And this allows you to leave this somewhere, leave it potentially. Maybe these spurious tones are very infrequent. You can hold it somewhere for a couple of minutes and then capture that and go back and analyze it and see all these different tones that appear in the spectrum, which of course shouldn't be there. We can also do a cumulative mode as well, which is a similar thing. It just shows you statistically where all the different tones appear. You can see them, the measurements are actually now dots on this, and various dots appearing as different different elements of the spectrum come into play. All of these are debugging tools allowing you to do this on the field. Same with the detector type, again, very straightforward. And of course, markers offer you very basic functionality here. In this case, the marker can be adjusted. You can place it anywhere you want, and you will get the marker measurement at the top left there. But it also now has a peak measurement, which follows the peak, which can be pretty handy, and it's very quick. So indeed, it does catch those tones that appear. Of course, this main tone that's sweeping is our largest tone, so it never catches any of the other ones. It'd be nice to, for example, be able to enter that I want the second largest tone. That can be very handy when you have a very dominant signal, which you all obviously know it's there, but you want to catch the second dominant tone, and that can be very good for debugging as well. But really, it's just some basic functionality of the marker, just like any other spectrum analyzer. And a few final remarks on the software here. You can do a full screen to get a better view of the spectrum, of course, and you can then lock the screen so it doesn't rotate if you're holding it in your hand. If you go under advanced settings here, you can actually change the way the USP behaves. So right now it's set to mass storage unit, so when you plug it into the computer, it will show up as just a storage, like a micro SD card. That way you can put files onto it, you can grab files out of it, you can even put your own files if you want. So this can be like a little USB storage that you carry with you as well on the field. If you change it to a serial port interface, it would allow you to connect it to the PC and do basically the software that acts like the firmware here directly on the PC, making measurements live on the screen. Becomes more like a PC connected spectrum analyzer. I've demonstrated that before. And in this version, you can also disable the charging. Perhaps you don't want the instrument to be charged from something you connect it to. If you have a laptop that, for instance, has very little charge left in it, you don't want the laptop to charge this as you're on the field. These are little tiny details, obviously done by people who have used these kind of instruments, so they know what kind of problems you may run into. Again, this is a very simple and lightweight operating system that allows you to do quick measurements. And there you have it. I hope you enjoyed this review of these instruments. Again, I like having these kind of things in the lab to do quick measurements and of course do these interesting experiments for you guys. As always, if you like it, please let the manufacturers know that you watch these videos and they help you make decisions on what kind of instruments to buy. It really doesn't benefit me other than having a good relationship with these vendors, and therefore I can bring you more of these fascinating instruments and take them apart and see how they operate. So if you have any questions, let me know in the comment section. I'll see you next time.